So I'm going to recap also what we have gone through up until 7.3. So we're covering this today and tomorrow. Tomorrow isn't necessarily anything different. It's just more practice with what are called separable differential equations. So in 7.1, we looked at what a differential equation was and we were verifying solutions. 7.2, we were finding or drawing the slope or direction field to then draw in a possible solution curve, but you're not actually finding the equation for the solution necessarily. In 7.3, and we actually work with these type of differential equations in 7.4 as well, the application part of it, we are actually looking at differential equations that can be solved. So you can actually find a function that is a solution to these differential equations. And these are called separable differential equations. So the first part of it is determining if it's separable. And then if it is separable, there's steps to actually solve it. But if it's not separable, you wouldn't be able to solve it this way. So what it means to be separable, and we're going to be practicing that part first. I think that's the maybe more difficult part to identify. A separable equation or separable differential equation is always a first-order differential equation in which the expression for dy dx or y prime can be factored as a function of x times a function of y. So that's important. It can be factored as a function of x times a function of y. So not a function of x plus a function of y, they have to be multiplied. So in other words, it can be written in this form. dy dx equals some function of x g of x multiplied by some function of y f of y. So if you can write it in that form, it is separable. So the name separable comes from the fact that the expression on the right side can be separated into two functions, one of x, one of y. And then these are the three steps. Your first step would be to separate the variables. So you want to get all of the y's on one side of the equation and all of the x's on the other side. So this is the part where actually, before we go through these examples, we're just going to practice this part. So if you're starting with, I'm just going to rewrite this here off to the side. If you start with dy dx equals some function g of x multiplied by some function f of y, in the first step, this is what it's going to look like. So when it's written like this, I want all y's on one side, all x's on the other. So I would divide both sides by f of y, or multiply both sides by the reciprocal of f of y. And then I'm also going to multiply both sides by dx to get the dx over here. So it would look like 1 over f of y dy equals g of x dx. So that would be step 1. And then hopefully by looking at this, especially with the dy and the dx, we have kind of the expression we would integrate written there. So that's step 2, is then to integrate both sides. So you take the integral of 1 over f of y dy, and that's equal to the integral of g of x dx. And then once you've integrated, technically you're done. You have the solution. But step 3, you should solve the equation for y if it's possible. So in some cases, you might have, based on whatever f of y was and that whatever that antiderivative or integral is, you might not be able to get y by itself, in which case you're done after step 2. Otherwise, you move on and actually solve for y if you can. Okay, so those are the 3 steps. So like I said, before we actually do any of the examples I have on here, I have the second page of the sheet that's attached here. I actually want you to turn to this page. I just want to have you practice identifying if something is separable or not. Because that is, I would say, a challenging part of this. Integrals we've been doing, so integrating each side, we've done integrals already. It's actually getting it to that point where you take the integral of each side. That's the challenge, in my opinion. So on this activity, there's 10 differential equations. Some of them are separable and some are not. So you are identifying if it's separable or inseparable, and if it's separable, you are separating it, meaning you're just doing that first step. So it does give an example, y prime, and if you see y prime, you can write that as dy dx. So y prime equals x times y, so that would be separable because you have x times y. So the function in terms of x would just be x, the function in terms of y would just be y. And then to separate it, they divided both sides by y, multiplied both sides by dx. So they got dy over y, which you could also write this as 1 over y dy, and then x dx on the other side. Okay, so that's all you're doing is just that first step in that 3-step process is separating it or saying that it's inseparable. So I'm going to go through at least 1 or 2 of these with you. So if you look at number 1, would you say that's separable or inseparable? Separable. So I'm going to rewrite this. The y prime is dy dx. So if you're saying it's separable, then we should be able to write it in the form where you get all y's on one side, all x's on the other. So what would that look like? Yes, so multiply both sides by square root of y and dx. So it is separable. You get to here, and then we would integrate each side. What about number 2? Separable or inseparable? Okay, so I'm hearing a couple different things. So what Danica is saying is x and y are being added together. So based on what we had talked about, or how I had mentioned it on this side, where you're multiplying each side by the reciprocal of f of y. So that could be either multiplying or dividing by your expression with y. Here we wouldn't be able to multiply or divide to get y on one side, x on the other. Yes, we could subtract, but I want you to see what that would look like. If we subtracted y from each side, then the left side would be dy dx minus y equals x. Now if we multiply by dx, we'd have to multiply this entire thing by dx. So you would have dy minus y dx equals x dx. You can't do anything with this. So you have to be able to multiply or divide your y expression to the other side. If you end up adding or subtracting terms to get y's on one side, x's on the other, that is not separable. So whatever is on this right side has to be a product or a quotient of x and y. So this is inseparable. Okay, so I want you to look at the remaining 8, determine if they're separable or not. If they are separable, then do that first step. Of the remaining 8, only 2 of them cannot be separated. Only 2 of the remaining 8, so 3 total. We already did 1 of them. So 2 of the remaining 8 cannot be separated. And you may have to rewrite the right side to see the separable form. So not all of them are set up for you to just do the multiplication or division right away. It's still a little subtracting to get the y on the other side. But that is the right step to rewrite this as this. You have the function that you add in So if you see something written as addition, you write it so that it's a pattern. The ones you say yes for, you should actually be doing that first step of separate.
What about the long back?
I don't think you do all this now. Right. So that I'm just telling you 5 is wrong. Yes, you have to see it, write it.
I'm not kidding. It's gone forever. Took advantage. What did you say? What? Oh, that one. No, I think it was 5. Five is acceptable. No, that was wrong. That's all. Well,
What about
oh. what? Right, everyone? Blow what? How many stop? Why how you not? What? 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 I think what? Wait. What? What? What's up? What's up? What's up? Oh, that's right, that's right. Hey, no, like 8th grade, like, Yeah. I don't know how you fix that. I don't know how you fix that. Well, I used to talk about that. I'll show you how you can. Oh, you just rearrange it? Oh, yeah, oh, you did. You rearrange it. That makes sense.
So what they're trying to do with these two is here you have a logarithm rule. They're trying to get you to think that you can do the same thing for
Stupid trick.
Okay. Just so we're able to get to the examples that we actually then work through, because like I said, this first step, actually separating it, that is a more challenging part of this. I first want to ask, before I show the answers, are there any that any of you are stuck on that I could just go through? Number 5. So for number 5, you can actually rewrite using algebra. I know some of you I talked with this about how could we rewrite this side for number 5. Danica? Okay. Yes, so when you're multiplying exponents or powers that have the same base, you can add their exponents. So I can rewrite this as y times e to the sine of x times e to the cosine of y. Because when I multiply these together, that allows me to add their exponents. So it's kind of doing the reverse of what you would normally do in algebra. But then because this is all multiplied, I could divide by the y and e to the cosine of y. So I would have 1 over y e to the cosine of y dy equals e to the sine of x dx. Does that make sense for 5? Were there any others that you were just stuck on? 7, yes, a few of you asked about 7 too. So here's 6 and 7, what they're trying to get you to think of. For 6 we can rewrite. You have a property of logarithms that allows you to bring that exponent down. So you'd have dy dx equals y times the natural log of x, which then now this is a product I can divide by y, so 1 over y dy equals natural log of x dx. So that's 6. They're trying to get you to think that you can do the same thing for number 7, but you cannot do that with trig functions. So 7 is actually one that's inseparable. You cannot rewrite that, so there's no way to separate the x and the y.
For you and your daughter.
There you go.
You gotta solve one of these.
Right.
And then you'll be like,
the ones that inseparable, you can be like, oh my.
Right.
and then put that, the last
That's
one,
the cutest
Mrs.
thing
Truesdale and
ever
Mr. Truesdale, and be like,
Right. All right. Any others that you are just stuck on? Otherwise, I will show the rest. Okay, so actually check if you were able to get through the rest that you have them correct. You don't want something in your notes that you have written incorrectly. So number 3, let's do this here. 3, you can rewrite natural log of x times y as natural log of x plus natural log of y, but it is a sum, so it's inseparable. I think walking around most of you, I saw 3, had 3. 4 is separable. Make sure you have the correct form when you separated the variables. So natural log of y plus y, that quantity times dy, and then the quantity natural log of x plus x times dx. And then 5 we went through. 6 and 7 we went through. 8 is separable. You can factor out a y and then divide by it. So 1 over y dy equals the quantity sine of x plus x dx.
oh.
So if you noticed with these, you're reviewing a lot of algebra or logarithm properties to see if things can be separated. Here's number 9. So you can factor from the numerator out a y, from the denominator an x, and then kind of rearrange your fractions into a product of a x fraction and a y fraction. So make sure, again, your separable form is correct. 2 minus 3y over y dy, x plus 1 over x dx. And the last one, you can factor by grouping. So you can factor by grouping, group the first 2, group the last 2, and factor out the GCF to see that you can factor it to x plus 1 times y minus 2. So 1 over y minus 2 dy equals x plus 1 dx.
Oh. Can you also write that from y over?
Yes. Questions? Okay, so like I said, that is a tougher part of these examples. So now let's actually look at a full example, since that was just step 1.
What? Let me guess. Separate this one.
Yes. Well, I'm not going to give you one to solve that isn't separable. I'm not going to trick you. Yeah. So for these, looking at example 1, I am not going to give you a differential equation and say solve it if you can't solve it. So I'm not trying to trick you, meaning you have to know that this is separable. That just means there is a way to separate it. If you're thinking there isn't, you have to figure out how to separate it. So step 1 is to separate the variables. We need the y's on one side, x's on the other.
Ooh.
How could we separate
I got it.
these? Yes, Jake.
You're going to multiply dx by both sides, and you're also going to multiply 2y plus cosine.
Yes, so you'd have 2y plus cosine y dy equals 6x squared dx. Okay, so that's what we just practiced. Separate the variables. Then step 2 when you're actually solving this is to integrate both sides. So I am now taking the integral of each side of my equation. Okay, now with integration, you have to remember antiderivatives, or you may need to use substitution. Yes. So for the left side, antiderivative of 2y. No. Y squared. You did 2y squared. That would be the antiderivative of 2y squared. And then cosine of y, antiderivative is sine of y, equals antiderivative of 6x squared, 2x cubed. Now, both integrals on both sides are indefinite. Yes, Liz? Oh, okay. Yes, they are both indefinite, meaning what do we need? A plus c. You do not have to put plus c on both sides, because if you did, and then you subtracted one of them to get your constants together, you'd still have a constant. So you just need plus c on one side. Normally, you'll put it on the side with x. But you have to remember the plus c. Has to be on one of your two sides. Okay, so now from here, this is your solution. However, if you can solve for y, you are required to. So AP free response question. You may leave your answer like this unless, if you can solve for y, they expect you to solve for y. So, can you solve that equation for y?
No.
No, because you cannot factor a y out of sine of y. So this is your solution. This would be an implicit solution. You are unable to solve for y. And this would be the general solution. Example 2 says, now for this solution in example 1, find the solution that satisfies this initial condition. So here's where we did this in 7.1. You would substitute in the x and y values to find your c. So in the solution I just found, I'm going to replace y with pi and then x with 1. So I have, no, I have pi squared plus sine of pi equals 2 times 1 cubed plus c, and I need to figure out what c is and leave c in its exact form. So we have pi squared. What is sine of pi? 0. So pi squared equals 1 cubed is 1, so this is just 2 plus c. So if I subtract 2, pi squared minus 2. Okay, and you would leave c like this. Okay, and then you rewrite this solution with c substituted in. So the exact, or the particular solution for this one is y squared plus sine of y equals 2x cubed plus pi squared minus 2. Now I will say also, if, say we could solve for y, and we'll be going through more examples tomorrow too, but if we could solve for y, once you get to this step, if you have an initial condition, I would always recommend you substitute in the initial condition and solve for c before you solve for y. So if we were able to solve for y, I would want to do this first and now from here get the y alone. Otherwise, you end up doing some backtracking if you solve for y and then try to solve for c. We will do examples where we will be able to solve for y. Any questions on this one? A differential equation is just an equation that involves a function and one or more of its derivatives. So if like you had an equation that involved velocity in the equation, that would be a differential equation because velocity is a derivative.
So the position and velocity is both of each.
So the position function would be the solution to it, but you might have like velocity in the equation. So it's just an equation that is written that involves one or more of a function's derivatives. This example 3, I know we only have a little bit of time, but there's something I want to talk about with how you write the solution quickly. So, how would you separate number 3? Divide by y, multiply by dx. Because remember, y prime is dy dx. So we would have 1 over y dy equals x squared dx. Once you've separated your variables, integrate each side. Yep, natural log of the absolute value of y equals 1/3 x cubed plus c. Can you solve this one for y? You can, even with the absolute value there, you can do that as well. So to get rid of natural log, we would raise both sides as powers of e. So this is gone. So I have the absolute value of y equals e to this whole thing. So e to the 1/3 x cubed plus c. That's all in the exponent. And then from here, this is not simplified. And I'm going to show you, especially when you're checking answers in the back, they would write this a different way. Because of the absolute value, that means, or rather to get rid of the absolute value, you include that this side could be positive or negative. So if I just put a y here instead of the absolute value, I would have a plus or minus on this side. So e to the 1/3 x cubed plus c. This still is not how they would show the answer. So think of, we just looked at this in one of our examples on just the separation side. When you add exponents, that means you are multiplying powers. So I could write this as y equals plus or minus e to the 1/3 x cubed times e to the c. Well, if it's you could, but if it's all being multiplied, the plus or minus applies to the whole thing. Now, why you would do this? C is a constant. E to a constant is still a constant. And actually, I could include the plus or minus in with this. So what you might see them do is say, I'm going to let, and they usually use the variable capital A. I don't know why, but that's usually what they use. You could use whatever you wanted to, but they can say, I'm going to let A represent plus or minus e to the c, because then I can write my solution as y equals A times e to the 1/3 x cubed, where A is plus or minus e to the c. Okay, so just showing you when and if you check an answer and it's written like this, where that A came from.